In this section, we are going to talk about revisiting rational number and their decimal expansion. We'll start with introduction, then we'll talk about terminating rational numbers and theorems associated to it. Then we'll talk about non-terminating rational numbers and theorem. And at the end, we'll look into some examples. Let's start with introduction. We all know from class 9 that a decimal expansion of rational number is either terminating or non-terminating but repeating. Right? That we have studied in class 9th itself. In this section, we will explore exactly when the expansion of decimal of a rational number is terminating and when it is non-terminating but repeating. Let's take an example of terminating rational number. So we have a number 3 by 8. We can represent 3 by 8 as 3 divided by 2 to the power q. And then we can multiply number 3 divided by 2 to the power q as 5q divided by 5q. And hence you can represent that number as 375 divided by 10 to the power q, which then can further be represented as decimal expansion 0.375. Now let's take another example, 134 divided by 100,000, which can be represented as 134 divided by 10 to the power 5, which then further can be represented as 2 into 5 to the power 5, which can be represented as 2 to the power 5 and 5 to the power 5. And 134 can be represented as 2 multiplied by 67. And hence 134 by 10 to the power 5 can be represented as 2 divided by 2 to the power 5 multiplied to 67 divided by 5 to the power 5, which then can be represented as 67 divided by 2 to the power 4 and 5 to the power 5. Here power of 2 and 5s are not same, and in this case power of 2 and 5 were same, right? So now here other things to remember. I can always assume 5 to the power 0 also associated to 2 to the power 3. Alright, now let's try to get into some understanding after looking into these examples, right? So these examples shows us how can we convert rational number of the form p by q. So I have a rational number of the form p by q, where q is of the form 2 to the power n and 5 to the power m, to an equivalent rational number of the form a by b, where b is power of 10. So if you can see, p by q was my rational number, in this case 3 by 8, and we finally represented them as 375 divided by 10 to the power q, which is again a and b, where b was power of 10. Therefore, the decimal expansion of such rational number terminates. So what it means, if you have been given a rational number of the form p by q, and you can represent q as power of 2 and 5 with different exponent, you can then represent that number very easily as a by b, where a replaces p after some modification and b replaces q after some modification, such a way that b will become a power of 10, and hence the decimal expansion will definitely terminate. Right? So if I have been given a rational number and the quotient of rational number, somehow I am able to break them as multiplication of 2 and 5 raised to some power, I can definitely conclude that this rational number will terminate. Now let's try to understand some theorem with the examples, right? So the examples in the previous slide has two important theorems to remember. Theorem 1. Let x be a rational number whose expansion of decimal terminate. So if I know there is a number x which is a rational number and whose expansion of decimal terminates, then x can be expressed in the form of p by q, where p and q are co-prime, and prime factorization of q is of the form 2 to the power n and 5 to the power m, where n and m are non-negative integers. So if I already know x is a rational number, and I also know whose expansion of decimal terminate, then I can definitely represent x as p by q, where p and q will be co-primes to each other, and q can be represented as 2 to the power n and 5 to the power m. Now let's take a look of another theorem. On the other side, let x equal to p by q be a rational number such that prime factorization of q is of the form 2 to the power n and 5 to the power m, where n and m are non-negative integers, then x has an expansion of decimal which terminates. So between theorem 1 and theorem 2 is basically, theorem 1 was saying that this has a decimal which terminates, and hence you can definitely represent them as p by q, where q will get converted into 2 to the power n and 5 to the power m. Theorem 2 talks about if I have a rational number for which q of the form p by q, for which q can be represented in the form of 2 to the power n and 5 to the power m, then you can definitely conclude the decimal expansion of that number will terminate. Now let's talk about non-terminating rational numbers. Let's try to convert 1 by 7 into decimal. When you try to convert 1 by 7 into decimal, and if you try to divide it, what you will see, remainders comes as 3, 2, 6, 4, 5, 1, and then it repeats 3, 2, 6, 4, 5, 1 for the divisor 7. So you will see it follows an unique pattern in the remainder. You can see the decimal expansion of 1 by 7 is not ending, and this repeats after 6 digits. And hence, this is rational number, but non-terminating but recurring. Also notice that 1 and 7 are co-prime, and hence the only common factor between them is 1. Now, do you think you can break 7 as multiple of 2 and 5? 7 is a prime number. You cannot further break it down into any prime factors. So you cannot. This is why you were not able to terminate decimal expansion of 1 by 7. Let's take a look of another theorem, which is our third theorem. Let x equal to p by q be a rational number such that the prime factorization of q is not, remember, it is not of the form 2 to the power n and 5 to the power m, where n and m are non-negative integers, then x has an expansion of decimal which is non-terminating, repeating, and hence recurring. So now, using theorem 3rd, you can always say a given rational number will have a decimal expansion which will non-terminate but repeat if you are not able to transform q as 2 to the power n and 5 to the power m. Now let's take an example. Try to find 17 by 8 is a rational number with terminating decimal or not. We can see 17 by 8 can be represented as 17 divided by 2 to the power q. And you can also see it is also multiplied by 5 to the power 0. Right? So 17 divided by 2 to the power q, 5 to the power 0. And hence, this was a number where q, which is 8, I was able to express them as 2 to the power m and 5 to the power n, where m is 3 and n is 0. And hence, this is definitely a number whose decimal is going to terminate. Let's take another example. Let's take 64 by 255. Can this be a decimal terminating number? Let's take a look. 64 by 255 can be represented as 64 divided by 5 multiplied by 3 multiplied by 17. And you can see all the three numbers are prime numbers, and hence you cannot break them further. And now I am at a point where q, which is 255, I'm not able to transform them as 2 to the power n multiplied by 5 to the power m. And hence, if I try to really find a decimal expansion of this number, I'm not going to get terminating decimal. Thanks for watching. You can visit us on www.classesfun.com.